This on? Yeah, yes. Okay, good morning, everybody. Welcome to our annual CGU Hydrology Section Plenary. For the benefit of new people in the room, people who are new to CGU at least, this is what we call the WU Lecture, and it is our attempt, I think a successful attempt, I hope, to honor the career legacy of Professor Minko or Hawk Wu, who was a professor at McMaster University for many decades and really pioneered a lot of the work in permafrost hydrology in Canada and produced a number of landmark contributions on that topic. And if you're interested in his life's work, I would encourage you to get his textbook called Permafrost Hydrology, which came out, I think, in 2012. It's a beautiful book, and a lot of his life's work's in that, but also a lot of work by colleagues in the field. Beyond his research contributions, though, Professor Wu is really well known for training and mentoring the next generation of hydrologists, many of whom went on to become really successful in research careers here in Canada, often focusing on northern hydrology. And some of them are getting close to retirement age too. So you continue to see the effects of generation after generation based on Professor Wu's leadership. So we're excited again to have another WU lecture this year, which brings us to this year's WU lecturer. Dr. Genevieve Ali is an associate prof at McGill University. She's cross-appointed in Earth and Planetary Sciences and Geography. Genevieve specializes in catchment hydrology, mainly focused on forested or agricultural systems, and she was just telling me she's setting up a bunch of new catchments in the coming year. Her research group uses both field data and remotely sensed data to look at catchment processes, especially rainfall runoff generation, contaminant export, and ecohydrology processes. And she studies a huge range of watershed sizes, which I think we'll get into a little bit today. Genevieve completed her undergrad and PhD at UDEM in Montreal, and then was a postdoc at Aberdeen with Chris Soulsby and Dorothy Tetzlaff, who have been WU lecturers here before, and also with Jeff McDonnell. And then she was at a couple other universities in Canada, and then landed back home in Montreal at McGill. Genevieve's had many critical research contributions. One common thread that goes through a lot of her key papers is the development of new methodological approaches, at least new in catchment hydrology. Her achievements have been recognized by many prestigious awards. Just a couple highlights here. She won the Science and Technological Achievement Award from the US EPA in 2022, the CGU Young Scientist Award in 2014, and the NSERC Early Career Award in 2013. I think it's also worth noting for those of us that know Genevieve, one of the things that stands out the most is her service to our profession. She's been editor, associate editor, or editorial board member for Scientific Reports, Journal of Hydrology, Hydrology and Earth System Sciences, and the Soil Science Society of America Journal. Recently was chair of the AGU Catchment Hydrology Committee, which is a pretty big role and important role internationally. And she's been in many other organizations, and then just this week became the outgoing chair of our awards committee here at CGU, where she's done a tremendous amount of work making the awards process more transparent. And so we're so thankful for her efforts to our field and for her contributions in research and her leadership. We are pleased to present Dr. Genevieve Ali as the 2025 WU lecturer. So Genevieve.
Hi, everyone, and thanks, Barrett, for the introduction. It is quite a pleasure for me to be here, although I will admit that it is a little bit intimidating to give this lecture, which is named after a giant in Canadian hydrology research. And so I've never actually worked with Hawk, but I had the pleasure of meeting him a few years ago during a visit at MAC. Hawk is really well known, as Barrett said, for his research on cold regions and permafrost hydrology, which is not my specialty. But there are a bunch of other facets of his work that I've been able to learn from through the years. And so, for example, Hawk worked across scales quite a bit, so focusing on individual wetlands, but also hill slopes and catchments, which is something that resonates with me and that I try to emulate as well. And then the part of Hawk's legacy that I identify with the most is his work on detailed process studies. And so in particular, the work that Hawk and some of his academic children have done on fill and spill dynamics, and connectivity has really had a profound influence on the way I frame my own research, which kind of relates to what I want to talk to you about today. So, like other process hydrologists, I focus on runoff generation mechanisms both above ground and in the subsurface, and most of our collective knowledge on runoff generation is actually coming from a relatively small number of experimental hill slopes and catchments. And so what that means is that I tend to rely on historical research outputs from those sites quite a bit. And so, for example, origin papers on saturation excess overland flow, variable source area concept have come from Coweta in North Carolina. The Mai catchments in New Zealand have been really critical in allowing us to make discoveries about shallow subsurface flow processes. You can think of macropore flow and pipe flow processes. Other field observatories like H.G. Andrews in Oregon and the Pinella site in Georgia in the southern US have also really helped build our knowledge of flow processes. And there are a few other really historically significant field observatories that exist throughout the world. And for those of you who are interested, you can read the details about some of them in a recent special issue of the journal Hydrological Processes. And what really distinguishes field observatories is their wealth of data. And so we're talking about sites for which we have high frequency, high density, multivariable measurements related to runoff generation. And I'm just going to give you one example of such, which is the catchment I did my PhD on. And so the Erie catchment is 5 hectares of forest on the Canadian Shield in Quebec. It is one of those really textbook experimental catchments where we have a V-shaped morphology that's centered around an ephemeral stream. Soils are developed from glacial till, and then we have throughout the catchment a shallow, low permeability soil layer above which we can actually have perch water tables form. And so there's been a lot of data collected in that watershed over the span of 2 decades, including data about hydrological inputs to the catchment, so precipitation and other meteorological variables, but also data about outputs from the catchment, so flow, hundreds of water samples collected from true fall collectors, suction cup lysimeters, and organic and mineral soil horizons, an autosampler at the outlet. And in addition to that, spatially detailed measurements of internal catchment state variables like soil moisture and water table depth were also part of the experimental setup. And what's really neat when we have such a rich data set is that it allows us to discover unexpected things, but also to find potential explanations for them. And so about 15 years ago in the Erie catchment, we discovered that in response to rainfall events, we had some elements like silica, cerium, strontium, and yttrium that were peaking before stream discharge. And then we had other elements like arsenic, selenium, and vanadium that were peaking after stream discharge. And so one of the first hypotheses that we had was that maybe that may be attributable to expanding and contracting patterns of saturated areas in wet versus dry conditions. And we had our detailed weekly soil moisture maps to investigate that hypothesis, but we found no relationship with soil moisture. So then we were able to turn our attention to our detailed maps of perch water table depth, as well as a map that we had recently created at the time of the depth to that shallow, low permeability soil layer I was referring to earlier. And it is then that we realized that contrary to what we had previously assumed, that shallow, low permeability soil layer actually had an irregular topography, which meant that we had a bunch of subsurface depressions that we didn't know about before. And those depressions could be dry or filling up with water or spilling. And so what we did at the time was that we took our depth to the water table data and we transformed it so that we could express it in terms of height of water in the subsurface depressions and basically document fill and spill dynamics that way. And so in this animation that you have here, each frame is a different sampling date. And then our dry depressions or empty depressions are in red. The ones that are filling up are in cyan, and then the ones that are spilling over are in blue. And so that data and that analysis made us realize 2 things. Number one was that the ephemeral stream was not actually flowing at the outlet unless we had at least a few of those subsurface depressions that were spilling. And then also, the depressions on the north and south portions of the watersheds were not always spilling at the same time. And it is that difference that explained why we had differences in the timing of the maximum trace element concentrations that we were seeing at the catchment outlet. And so this was just an example to show that such rich and diverse data sets are really the ideal setup for inferring runoff generation mechanisms. And so we need to maintain field observatories as much as possible and create new ones as much as possible as well. That said, there are data and knowledge biases that are associated with field observatories, and some of those biases are readily available from the pictures that you can see here. So the vast majority of our field observatories are actually forested hill slopes and catchments in temperate, humid environments where we have at least 70% of annual precipitation that falls as rain. And so what that means is that in comparison, we have very few catchment scale agricultural observatories, which is still preventing us a little bit from appreciating the impacts of different agricultural management practices on not only runoff generation, but downstream water quality. And we have few cold regions field observatories outside of permafrost regions. But then really the most important bias associated with existing field observatories is their size, because again, it's mostly at the plot, hill slope, and small catchment scale that we have good data about hydrological inputs, outputs, and internal state variables, which is at odds with the larger watershed scales that form the basis of water and nutrient management, and for which we typically only have input and output data available. And those larger watershed scales are also the scales at which we devise mitigation strategies when it comes to fluvial flooding, or eutrophication. And so what that means is that on one end, we have a select number of small catchments for which we have high frequency, high density, high dimension data sets that we use mostly for experimental research purposes. And then at the other end, we have quite a large number of large watersheds for which we only have low frequency, low density, and low dimension data sets. We know from decades of research now that larger watersheds are not just the sum of small catchments, which means that upscaling is not a simple additive process. And so in that context, I guess what I'm wondering is whether if upscaling findings is difficult, then maybe what we should try to do in order to bridge the scale gap is to transfer methods rather than findings. But then that raises two questions. Number one is which methods or tools or concepts from small scale studies are quote unquote easy or relatively easy to apply to larger scales? And then the second question would be about whether there are research opportunities related to runoff generation that would be unique at larger scales and not necessarily present at smaller scales. So I'm sure that pretty much everyone in this room would come up with different answers to those questions, but there are three main concepts or tools or methodologies that we've been looking at to answer them. So hydrologic connectivity, precipitation threshold, and flow thresholds. And so that's basically what I'm going to spend the rest of my time today discussing. Okay, so first off, what is connectivity and why do we care? In hydrology in particular, we tend to talk about connectivity as the probability that a source location A would be able to transmit some material to a target location, let's call it B, while overcoming any kind of material losses that may occur along the way. And so in hydrology, we tend to describe connectivity either longitudinally between upstream and downstream locations, or laterally between hill slopes and streams, or vertically between surface and subsurface locations. There are a lot of definitions of connectivity in the literature, and some of them are more specific when they're tied to a particular quantification approach. And so here, this is a definition that is quite popular in forested field observatories because it focuses on subsurface flow-driven connectivity. And the diagrams that you have at the bottom there are just a schematic illustration of an old data set of ours from agroforested, yes, watershed in Manitoba. And so in this watershed, we actually measured stream water level fluctuations and water table fluctuations along riparian to stream transects every 15 minutes. And basically at that site, we interpreted the presence of a riparian to stream hydraulic gradient as an indication of lateral connectivity being present. Another popular definition that's, I guess, a little more static and based on snapshots of data is this one here, when we're trying to quantify the presence of active water flow paths between distinct watershed locations. And so with the two cartoons that you have here on the left-hand side, you would have a small number of active water flow paths, which are the white lines. And so there would be a low degree of connectivity. Whereas on the right side, you have a lot more of those. And so that high degree of connectivity is made possible because enough precipitation water was fed to the landscape in order to activate a high enough number of flow paths per se. And so connectivity is important for process understanding, but it also has the potential of being really important for water management and policy making. And I guess the example that I often give is this one here. So if we had a landscape like this with known water quality issues at the downstream end, then the challenge would really be to pinpoint which pollutant sources in the landscape are hydrologically connected to the outlet, so that we could potentially target those sources for remediation. And so when we use a definition and a quantification approach to connectivity that are spatially explicit, it allows us to answer the question, what should we do where in terms of management? And again, thankfully, we can rely on lots of research from small-scale field observatories when it comes to spatially explicit quantification approaches to connectivity. So I'm going back to my PhD days again. I think that's my last PhD example. And so for the small-scale forested marine catchment I was talking about earlier, we basically determined that active areas were areas that had soil moisture above 0.3 cubic meter by cubic meter. And so because we had weekly spatially detailed maps of soil moisture, we could decide to organize them in order of increasing wetness areas, or we could rather distinguish them based on whether the active areas, which are the black square, were spatially adjacent or spatially contiguous or connected to the catchment outlet. And so until a few years ago, there were quite a lot of studies like this one at small scales, but very few, if at all, at larger scales, which then pretty much begged the question of whether we could apply a similar approach, but to larger systems as well. So we decided to look into that a few years ago, focusing on the Lake Winnipeg watershed, and this was work that was done with former research associate Carolyn English, and there were 3 steps to our approach. So in step 1, we wanted to quantify the presence and connectivity of surface and near surface runoff across the 1 million square kilometers of land that make up the Lake Winnipeg watershed. And so for that, we used satellite-derived soil moisture data, and we applied spatially explicit connectivity metrics to that data. For our step 2, we wanted to quantify the magnitude of algal blooms in the lake, and so we relied on satellite-derived chlorophyll data. And in step 3, we basically wanted to bring everything together and answer the question that you have on the screen there. So we wanted to know which watershed locations need to be hydrologically connected to rivers before we see major algal blooms in the lake. And so for step 1 of the analysis, we relied on 160 something, I think 65 soil moisture maps that were derived from CMOS data. So data from the soil moisture and ocean salinity satellite. Our study period was 2010 to 2017, and we had about 20 to 24 images per year. And so those are the ones that you can see in the top animation there. So from that, we decided to combine those soil moisture maps with soil hydraulic information that we gathered from publicly available databases so that we can infer runoff activation and runoff connectivity. So I'm going to skip all the methodological details here and just say one thing. So in order to consider a pixel to be hydrologically active, we needed its soil moisture value on any given day to be greater than its field capacity. And then for that pixel to be considered hydrologically connected, it needed to be active and spatially contiguous or spatially adjacent to a stream of 3rd order and higher. And so the result of our assessment is in the bottom animation now this time. And so each time you see a pixel or a cluster of pixels pop up in blue, that means that we deemed it to be hydrologically connected based on our definitions and our criteria. And so you can see that throughout the 7-ish year period, there are some areas that remain in gray pretty much all the time. So those were areas that were never deemed to be hydrologically connected to streams. Otherwise, you have some areas that are popping up in blue really, really often or really frequently, and then others that are, yes, popping up in blue, but in a more selective or in more infrequent manner. And so again, for the sake of time, I'm going to skip a bunch of methodological steps just so that I can get to the last one, where we really wanted to compare the frequency of land-to-stream connectivity in the watershed to the magnitude of algal blooms in the lake. And so on this map here, the bright blue locations are those that were connected to rivers frequently, at least once a year, but typically multiple times a year. Whereas the green ones were those that were connected to rivers in a more selective manner, so infrequently. And what we realized was that in order for major algal blooms to be observed in the lake, we actually needed at least 50% of the green location to be connected to rivers for at least 8 weeks during the open water ice-free period. And so you may be wondering what makes the green location special. And our hypothesis at the time was that it was their position within the network of water flow paths. We often look at watershed drainage areas as contributing areas, but we do have to acknowledge that within those areas, we could have hundreds or thousands of runoff producing locations that are not all made equal, and that could behave quite differently depending on where they're positioned within the network. And so those green nodes here are critically located in the sense that they have the ability of either connecting entire upslope areas to rivers or disconnecting entire upslope areas to rivers. And so because of that critical position, we tend to refer to those locations as water gatekeepers because they're critical nodes. And so what that case study basically showed us was that it was at least technically possible to take an approach that had worked really well before at small scales and just swap field data with satellite-derived data in order to estimate the frequency of hydrologic connectivity over larger scales. And one potential management application may be that we could actually focus on water gatekeeper locations, given that they have a disproportionate influence on the network as a whole. We could actually target them if we want to promote hydrologic disconnectivity. And so if we want to establish infrastructure or establish management practices that will prevent excess runoff and contaminants from actually traveling downstream. Now, one big limitation of that study was the fact that we were not actually able to be really precise in the location of the gatekeepers because we're relying on a satellite-derived soil moisture data set that had a coarse resolution, so 15 kilometers. The good news is that since our paper was published, there have been quite a few new satellite-derived products that have come online and are now publicly available and that have much finer resolution as well. And so we do have the opportunity of repeating that exercise, not only in the Lake Winnipeg watershed, but elsewhere as well. And I have members of my group right now that are trying to do the same thing in the Lake Erie Basin, just for example. Okay, the second concept I wanted to talk to you about today is that of precipitation thresholds. And so generally speaking, a threshold would be, I guess, a critical point, either in time or space, that leads to an abrupt or sudden change in behavior. And the hydrology literature is really, really full of them. And so typically, again, according to the current literature, we don't see lots of behaviors like this, where we have a linear relationship between hydrological inputs, so precipitation, and hydrological outputs, so flow. Most of the time when we see our relationships look something like this, where there's little to no flow generated until a critical value of either precipitation or soil moisture is exceeded. And then once this is done, then we have flow generated, and that is what is highlighted in blue. And so precipitation thresholds are just one type of hydrologic thresholds, and we typically deem them to be present if there is a precipitation event characteristic value that causes a nonlinear change in a runoff response characteristics. So one of the reasons why we care and we're interested in precipitation thresholds is because they're related to connectivity. And in fact, precipitation thresholds are often thought to be indirect evidence of sufficient connectivity being established in the catchment to trigger flow changes downstream. Now, another reason why I think we should care about precipitation thresholds is because they could potentially be used as an indicator of change in hydrologic function, especially after disturbances. And so there was a really neat paper published about a few years ago, that was during the pandemic years, that showed that precipitation thresholds changed significantly after a catastrophic ice storm event in southern China, and that event actually led to significant changes in forest structure. And so we could imagine a situation where, in a Canadian context, a logging disturbance would cause a shift to a lower precipitation threshold, and maybe a wildfire disturbance would cause a shift to an even lower precipitation threshold. And so as long as precipitation thresholds exist, they could be used to compare the resistance and the resilience of different watersheds to a whole suite of disturbances. Now, again, most of what we know about precipitation thresholds is coming from small-scale field observatories. And so for those sites, we typically have data about input, internal, and output variables, output processes, I guess, at a sub-daily timescale. And so the approach is typically to take those data, to perform precipitation runoff analysis, and so focus on individual events so that we can then calculate event metrics and then look at the relationships between event metrics. So if you focus on the diagram that I have on your right, typically what we have as the dependent variable will be any event metric that quantifies runoff. And then on the x-axis there, we'll have an independent variable that's related to hydrological inputs or hydrological state variables, or a combination of the two, again, on an event-specific basis. And then what we do is that we fit either a segmented regression or a piecewise regression model to the data so that we can identify whether there is a critical value in the independent variable that causes a nonlinear change in the variable on the y-axis. And so this is just an example of what the analysis can look like, and those examples are coming from the PhD work of Cody Ross. And so what Cody did was to basically gather data from a bunch of field observatories in Canada, the US, Australia, and New Zealand, and he was able to show that piecewise regression often, but not always, led to the identification of precipitation thresholds. And those precipitation thresholds could signal a shift either from no runoff generation to some runoff generation, or a shift from slower runoff generation to faster runoff generation based on the change in the relationship slope there. Now, when we want to try and move on from small scale field observatories to larger watersheds, what we have to contend with is the fact that we typically don't have a lot of internal state variable data available. And then when we have input and output data, it is available at the daily resolution and not the sub-daily resolution, which in that case begs the question of whether precipitation thresholds still exist at larger scales and whether they can be detected using exactly the same methods that we're using at smaller scales. So this is something that we started looking into, I guess, late last year in Quebec. So we've been focusing on 124 watersheds that are ranging in size from about 1 square kilometer to 146,000 square kilometer. And so on this map, the bubbles correspond to the outlets of those watersheds. And we've been pretty strict, I guess, with our site selection in the sense that we only focused on sites that had at least 40 years of data. And so 40 years of daily water input data that we're getting from the graded climate data set DMAT, and then daily river flow data that we're sourcing from the Water Survey of Canada. And so from that data, what we've been doing for each watershed is to basically delineate individual water input events, so rainfall events, snowmelt events, rain on snow events, and mixed precipitation events, and then identify the flow responses to each of those events, calculate a bunch of event metrics, and then look at the relationships between the two to see whether we can detect any kind of threshold. Now, we did not want to presume, given that this is a scale that we're not used to, we didn't want to presume that precipitation thresholds would be present everywhere. And so regardless of the input-output data pairs that we've been considering, we fit 2 models to the data, a linear model and a piecewise linear regression model. And then there were 3 main interpretation scenarios that we're looking at. And so if both models were providing us with R-square values below 0.45, we deemed the input-output relationship as unclear. If the linear model was providing the highest R-square, we concluded to a linear input-output relationship. And basically, we only concluded to a threshold-driven relationship if the R-square of the piecewise regression model was the highest, and the piecewise regression model was performing significantly better than the simple linear model there. So I'll just get into what our results look like step by step. So on this slide, I'm focusing on rainfall events only. Our output variable is the total event runoff, and then our input variable is a combination. So that's basically total event precipitation to which we add the cumulative water input from the 7 previous days, and from which we subtract the cumulative potential evapotranspiration from the previous 7 days. And so on the map, you can see what it is that we found. Results were not very conclusive at all. So most of our watersheds, we concluded to an unclear relationship. Those are the black dots. And then we had about a dozen watersheds with linear relationships in blue, and then a single threshold-driven relationship. Now, we are focused on Quebec, where we know that seasonality effects are really, really strong, and so it was not really reasonable to assume that a single model would actually perform well across all seasonal conditions. And so from this step, we decided to break up our data by season, and then things got a little more interesting. So here, I'm looking at exactly the same pair of input and output variables as before, except that we're doing that 1 season at a time, focusing on rainfall events again. And so there were still quite a high number of watersheds for which we determined an unclear relationship. Those are the black dots that were especially present in northern Quebec and then in the spring season. Otherwise, in southern Quebec, winter was the season with the highest number of linear relationships identified. Those are in blue. And then summer was the season with the highest number of threshold-driven relationships identified. Those ones are in yellow. That said, we still had quite a bunch of watersheds for which we couldn't find anything interesting. And so we wondered whether we should actually change conceptual models. The literature is quite rich in examples of watersheds that are driven by one threshold, but we're wondering whether some of our watersheds might actually be driven by two thresholds. And our alternative model here is that when we exceed the first threshold, which is the runoff initiation threshold, that may be an indication that we have land-to-stream connectivity that is established in the catchment thanks to at least one runoff generation mechanism. And then when we exceed the second threshold, which is the rise threshold, that could mean one of two things: either that the spatial extent of connectivity has increased significantly in the catchment, and or that additional runoff generation mechanisms were actually activated, therefore triggering flow changes downstream. And so we looked into that using the same data set, and then our results changed a tiny bit. And so here I'm focused on exactly the same input and output variables again, rainfall events only, one season at a time. So for winter, spring, and fall, the number of unclear relationships didn't change at all. What changed was that some watersheds that were previously well described by a one threshold relationship were better described or ended up being better described by a two threshold relationship. And then in summer, one thing that was interesting was to see that there were some watersheds that were previously associated with an unclear relationship that then became pretty well explained by a two threshold relationship there. Now, another thing that we wanted to test is the fact that our ability to detect precipitation thresholds really depends on what we consider our input to be and what we consider our output to be. And in fact, picking an input-output variable pair is kind of the equivalent of putting forward a hypothesis about what the dominant runoff generation mechanisms are and what the main drivers of runoff generation are. You could, of course, think of a distinction between looking at precipitation input in terms of amount, total amount, or looking at precipitation input in terms of intensity. So that would be a distinction between storage-driven runoff generation processes and intensity-driven runoff generation processes. I'm talking too fast. And so we did that. We wanted that analysis to be as comprehensive as possible. So basically what we decided was to be as inclusive as possible in terms of the number of input-output data pairs we considered. So we considered 4 different options for the output and 43 different options for the input, which means that for each watershed, we basically tested 172 pairs of input-output variables. And we just wanted to know whether for any watershed, there would be at least one of those pairs that would lead to a threshold-driven relationship. And so when we did that, in summer, we realized that for summer rainfall events, we had at least 73 watersheds out of 124 for which we could detect the threshold-driven relationship. And that was the case for really small watersheds, about 1 square kilometers, but also our largest watershed, 146,000 square kilometers. We were able to detect threshold-driven relationships with that one as well. Now, when we moved to the fall season, the number of watersheds for which we detected the threshold-driven relationship dropped to 63, and that number further dropped to 38 for the winter season and then 27 for the spring season. So as I alluded to really quickly earlier, this is work that we just started last year, and so we still have a lot of results to actually come true, as you can imagine. But what has been interesting for us to realize to date is that piecewise regression analysis, which is really simple and not fancy at all, is actually allowing us to detect precipitation thresholds at really small scales and at relatively large scales as well. Potential management implications that we're kind of thinking about at this time are, well, there are 2 of them mainly. One of them being that depending on whether the threshold is associated with a precipitation intensity variable or a precipitation amount variable, we may be able to rely on that to infer dominant runoff generation processes at large scales. Another thing that we think could be interesting is in the context of not only climate change, but land cover changes as well. We may be able to come up with return periods, current and projected, for precipitation intensity thresholds and precipitation amount thresholds. And if we were able to do that, then we could potentially devise a management or adaptation strategies around that. Now, this is not a type of study that is without limitations, and in fact, there are quite a bunch. And so one of the most baffling results to date for our Quebec study has been our total inability to detect anything north of the 49 parallel. And so we basically need to figure out whether this is real or whether this is data-driven. And we have a bunch of different ideas of about why that may be. We're also very well aware that at those types of scales, we're using daily data, but that daily data might be completely masking really flashy behavior that's occurring at sub-daily timescales. And so what that means is that anything that we identify in terms of precipitation threshold is going to be biased either towards non-flashy watersheds or multi-day events. And then, of course, we still need to go through the details of our results for rain on snow events and mixed precipitation events because we're seeing different patterns there. So the last thing, or the third thing that I wanted to talk to you about today is flow thresholds, so different types of thresholds. But before I get to that, I need to provide maybe a little bit of a background in the context of chemical exports from watersheds. And so we all know that runoff can mobilize solutes from a variety of watershed sources, and quantifying those solute movements is really, really important. Ideally, we would actually do that within a source pathway receptor framework. Basically, what that means is that we would have detailed data about the watershed sources, the receptor locations, and then the transport mechanisms that allow solutes to travel between the two. Most of the time, though, our detailed data about water flow rates and then concentrations are only available for the receptor location. And so that is why we tend to rely on concentration discharge relations or CQ relations quite a bit. So the literature, and there have been quite a few really interesting talks this week already about CQ relationships. The CQ relationships are really, or CQ studies are really popular in the literature because those relations are thought to provide information about the hydrological and biogeochemical processes that control runoff chemistry and downstream water quality. One of the challenges is that in order for us to be able to make process interpretations, we actually need to fit the mathematical model to the CQ data. And there's quite a variety of mathematical models to choose from. And so a few years ago, my group teamed up with Henry Wilson and Jane Elliott just so that we could test 6 different CQ models on the same data set. And so we were focused on 32 Manitoba watersheds at the time, and then we were mostly interested in total dissolved phosphorus dynamics. And so this is one of the figures from the paper. It's really busy, but don't worry, there are just a few things from it that I want you to pay attention to today. And so the rows correspond to the 32 Manitoba watersheds that we focused on. The columns are the 6 different CQ models that we tested. And then the colors are proportional to the R square of the model. And so we're basically going from very poor model performance in the dark red to, I guess, fair to good to very good performance in the yellow, green, and blue shades. And so at the end of that exercise, we basically realized that a lot of the model performances were not good. But the 2 models that appear to perform the best for the highest number of watersheds were the parallel model and the hydrograph separation model. So the parallel model is the one that is the most popular in the literature because it allows us to distinguish watersheds that are chemostatic versus chemodynamic. So chemostasis here refers to quasi-invariant concentrations despite varying flow conditions. And that's something that typically signals either historical buildups of solutes in soils or legacy sources. And then chemodynamic behavior is when you have concentrations that do vary with flow conditions. And then the hydrograph separation model is very different. This is one that relies on the premise that solute export is actually threshold driven. And so since we published that paper, there have been quite a few studies that have suggested to merge the 2 models. So go with the popular parallel model, but acknowledge that CQ relationships or CQ dynamics are not actually constant across all flow conditions. And that is where flow thresholds actually come into play. So if we were to go with the assumption that CQ behavior doesn't change across all flow conditions, then we have 3 options available. So it would either be that concentrations increase monotonically with flow, so that's enrichment, concentrations decrease monotonically with flow, so that's dilution, or we would have constancy there in the middle. Now, if we rather assume that CQ behavior changes depending on whether we're at low flow or high flow, then we have 9 different possibilities, and those are associated with different CQ slopes below and above the flow threshold. And because we're dealing with different CQ slopes, we tend to refer to those behaviors as dual behavior, a dual slope behavior. And so in the literature to date, the CQ slope has really been touted as a potential effective watershed management tool because it basically tells us about the watershed's ability or tendency to store and to transport chemicals, which is great. I guess what I'm trying to figure out here is whether a flow threshold, when it exists, would also be a valuable management tool simply because it signals the flow value above which either solute sources change or the runoff mechanisms that are mobilizing those solutes change, or both change. And this is something that has not been studied extensively to date, especially not in a context where multiple solutes may actually be of concern. And so one of the questions that we're just started investigating here is whether in a single watershed, CQ slopes and flow thresholds are consistent among water quality parameters. And the idea here would be that if they're consistent, that may be an indication of similar sources and or similar mobilization mechanisms, whereas if they're dissimilar or they're not consistent, then we have really complex solute behavior to deal with. And so this is really, really, really recent work. We literally started that in January of this year, and so our results are super preliminary, but we've been able to piggyback on work that was done by former postdoc Sarah Ariano until last October. So we've been focusing on 32 Quebec watersheds, but today I'm only going to highlight 2 contrasted ones. And so one that is 79% agricultural, and then the other one is 75% forested. And so for that, we're using, again, publicly available data because some of those watersheds are really large. And so in Quebec, we have quasi-monthly water quality data available. And that data set is really rich and interesting in the sense that we have biological water quality parameters like fecal coliforms, that's the FC, and chlorophyll A. We have physical water quality parameters as well, and so suspended sediment, turbidity, electrical conductivity. We have a bunch of nutrient species as well, so dissolved organic carbon and different forms of nitrogen and phosphorus. And we have a range of major ions as well that are available. So here I just highlighted calcium, chloride, potassium, magnesium, and sodium. And so our methodological approach so far has been to take the CQ data for a given watershed and then first fit a piecewise regression model through it to see whether there is a flow threshold that exists. And then based on the result of that analysis, we then fit a parallel model to the CQ data, either a single model if there is no flow threshold, or 2 different models with different slopes if there is a flow threshold. So for the agricultural dominated watersheds so far, we found that there were only 5 of the water quality parameters that didn't have a flow threshold associated with them. Those are the ones without the asterisks. Otherwise, all the other ones with the 2 red asterisks are the ones for which we did detect a flow threshold, and so we had to fit a dual slope model to the data. Conversely, the forest-dominated watershed showed that the majority of the water quality parameters were not actually associated with flow threshold at all. And so once we had that done, the next step was to look at the actual value of the flow thresholds to see whether they can provide us with any kind of interesting information. And so for the agricultural dominated watershed, which is this one, we noticed that the biological water quality parameters, which are in orange, and the physical water quality parameters, which are in yellow, either had no flow threshold associated with them, or when they did, that flow threshold was lower than the long-term median flow value for the watershed. All P forms, so all phosphorus forms and nitrogen forms were associated with a flow threshold, and that flow threshold was greater than the long-term median flow value for the watershed. Now, for the forest-dominated watershed, as I mentioned really quickly before, for most of the water quality parameters, we had no flow threshold detected at all. The only 3 exceptions were nitrate, nitrite, ammonia, and chlorophyll A. And then what has been really surprising to us so far is that for those 3 species or those 3 parameters, the flow threshold was not only greater than the long-term median flow value, but it was in fact greater than the 95th percentile of flow, which is a bit strange. And so I guess our preliminary data analysis based on those 2 watersheds, but a few others as well, show that yes, there are flow thresholds that are different between water quality parameters. And some of them are associated with quote unquote low flow conditions, whereas others are associated with high flow conditions, which is a little bit puzzling, but which may just hint at really complex solute behavior. So we still have a long way to go in terms of that type of analysis here, but I guess what we're trying to figure out is whether combining flow thresholds with CQ slopes may help us get a better feel for how complex multi-solute export behavior may be in some watersheds. And we're also thinking that that combination may help us identify or distinguish watersheds that are difficult to monitor versus difficult to manage based on the type of dual slope behavior we're actually dealing with. One thing that we can see as a limitation already is the fact that so far our ability to detect a robust flow threshold has really depended on the frequency with which water quality data is actually monitored. And so for our Quebec data set, we're quite lucky in the sense that most of our data is available on a quasi-monthly basis, but we're very well aware that for most publicly available water quality monitoring programs, the monthly frequency may not be achieved. So I will start wrapping up here by just going back to the two questions I had when I started. So one of them was about tools or concepts or methods from small scale studies that could be applied to larger scales. And then the second question was about potential unique research opportunities at larger scales. And here by larger scales, what I really mean is anything that is larger than our typical field observatories, but also something that is large enough to actually include a diversity of soil characteristics and land uses and land covers as well, because management becomes really difficult when we have to deal with a mosaic of land covers, for example. And so over the past few years, I guess we've been trying to figure out whether connectivity, precipitation thresholds, and flow thresholds have definitions and quantification approaches that are flexible enough so that we would be able to apply them at larger scales. We think it may be possible to a greater extent. The one thing that we need to still figure out is how to incorporate data uncertainty that is very significant at larger scales, how it is that we can incorporate that into our analysis so that we could nuance our results and our conclusions accordingly. The one question I haven't touched on yet has to do with whether there are unique research opportunities at larger scales, and I think there are, and potentially as a community, we may want to focus on some of them a little bit more. And so when it comes to connectivity, for example, one question I have is about whether there are particular physiographic settings that would have a tendency to lead to water gatekeepers being present. And so those physiographic settings could be related to land cover, soil characteristics, macrotopography, which we tend to focus on quite a lot, but microtopography as well, which we tend to focus on a little bit less. When it comes to precipitation thresholds, I wonder whether their drainage area extends beyond which either the thresholds do not exist, or they may exist, but they may not be detected with the very simple piecewise regression approaches that we've been using for the past decades. And then if we were to kind of consider all three examples I gave today together, I guess one question would be whether water gatekeepers, precipitation thresholds, and flow thresholds can be used as indicators of hydrological change. And if they can, I guess a follow-up question would be, are there some that are more or less suitable to use depending on what the driver of hydrological change actually is? Just quick disclaimer, I have no idea what the answers to those questions actually are, but I think that we may get a better chance of getting to those answers if we do way more meta-analysis of existing data as we're currently doing as a discipline, and also if we systematically report the successes and the failures of those exercises. They're really time-consuming, and I think that we would definitely learn more from the failures and the successes as long as they're reported, of course. So I think that's all I wanted to talk to you about today, so thank you very much for your attention, and I'll be happy to take questions.
Is this one on? Great. Thank you so much, Genevieve, for that really interesting and engaging talk. So inviting questions from the audience now. So just raise your hand and I can run a mic to you. Yeah.
Thanks, Genevieve. That was really interesting. It was a great talk. I'm still kind of formulating my question in my head, so it may come out a little jumbled, but there's been a lot of discussion or presentation of the concept of chemical cocktails in some of the, I see it in the urban water quality literature, some of the Maryland researchers. And what I kind of gather from those is like if you're kind of just measuring concentrations in the stream, and you can kind of lump certain analytes together and kind of use those to inform management. But what I see with your CQ work is like it's not that straightforward. Like I was seeing ions having different models and different parameters that I know would get lumped in the chemical cocktail framework are actually clearly have different transport pathways. And so I'm just sort of, I don't know what my question is, but from like a management perspective, is there a risk in taking maybe these simpler cocktail approaches? And
So
where's that balance between understanding detailed transport pathways and like what kind of data we can actually access?
Yeah. So that's a great question. And I'm not sure I have the answer yet. I'm hoping that the kind of work that we're doing right now on the CQ may help us get there. But one parallel I see between your chemical cocktail idea and what Quebec is doing, for example, is that they have an aggregated water quality index that does exactly what you're actually saying. And so everything in terms of establishing priorities for monitoring, for management, for mitigation, et cetera, is actually based on that aggregated measure, kind of ignoring that all the different parameters that are incorporated into that aggregated measure are actually behaving completely differently. And so the solutions or the mitigation options should probably be different. And so one of the reasons why we're focused only on Quebec watersheds for now, we only have 32 that have enough data for us to do what we want. But the reason why we focus on that for now is because there is a lot of detailed watershed data that we're hoping will help us make sense of what those patterns actually look like. Like, for example, something that is publicly available is parcel-specific, year-specific crop inventory data, as well as drainage information. That's something that the farmers are obligated to report to the provincial government, otherwise they lose their provincial funding. And so we have that. And so that may help shed some light on why, for example, some of the major ions are behaving completely differently. Because again, even when we don't think of the chemical cocktails, we tend to go with those classifications of geogenic versus non-geogenic solutes, as if all geogenic solutes were behaving the same way, but we know that often that's not necessarily the case. And when we have mixed land uses on land covers, things get even more complicated. And so we're hoping that once we're done with the CQ analysis, we'll be able to couple that with the geospatial / watershed characterization analysis that Sarah in particular has done for us. Noel?
I saw another back there.
Okay, thanks Genevieve for the awesome talk. In the rainfall runoff analysis you did, you said you were working with daily data and it would be interesting to look at hourly. But I'm wondering whether it'd be interesting to also look at integrating over longer timescales, you know, weekly, monthly, or whatever, and maybe stronger patterns might come out.
Yeah, so it may. I think, and that's where sometimes what we do in field observatories is or at small scales, is real helpful and informative, but sometimes we're constrained by it a little bit. And so because we tend to have sub-daily data available in those field observatories, well, not all, but most of the threshold analysis or the threshold studies have been based on event data. But as you said, there's nothing that prevents us from looking at, I don't know, weekly data and see whether thresholds emerge, and then monthly data to see whether thresholds emerge, and then monthly data, seasonal data based on calendar seasons, or seasonal data based on growing, non-growing season, especially in agricultural environments when we know exactly when the crops were seeded, not seeded. We can actually come up with really precise definitions of what the growing versus non-growing season is. And so, yes, there's nothing technically that prevents us from doing that. So we should look into it.
Thank you very much. Very interesting talk. I must admit, I'm not a field hydrologist, so I'm not as familiar with the literature. One question I had is, could the sites further north, or the catchments further north, potentially be more snow-dominated rather than rain-dominated, and that could be contributing perhaps to some of the different results that are occurring?
Yeah, so that's a good question. I did not show any of our rain on snow event data or melt event data or mixed precipitation data. because the patterns are kind of similar in northern Quebec as well. And so what we're thinking, but we need to dig into that deeper, what we're thinking maybe the cause of us not detecting anything right now is first, the uncertainty in the gridded climate data might actually be worse up north. DayMed is providing some kind of uncertainty estimate, which we haven't looked at yet, and so we definitely need to do that. There's also the fact that a lot of the streams and the rivers in northern Quebec are dammed, and so that may be a big contributing factor, and so for that, we actually need to pull information from 2 different databases. There is information in the HIDAT database about whether the stream is quote unquote regulated or not, but in the Quebec data, which is different and the station numbers are different, et cetera, so we need to reconcile that. But in that database, there's actually more information about whether the flow regime is quote unquote daily influence or influence on a daily basis versus a monthly basis. And so we need to pull all of that together to try and figure out whether that explains what we're seeing. There's also, I guess, more uniform land cover in northern Quebec. So yeah, there are a bunch of different things that we kind of need to put together to try and see whether that explains why there's such a stark distinction between what we have in southern Quebec and then what we have up north. Sean.
Thanks, Genevieve. I was just wondering that if you think for these really large catchments, there's a point where sort of in-stream biogeochemical and hydraulic processes become like a dominant order factor on these threshold responses.
Yeah.
Because it's like
Yeah.
at huge scales.
Yes, definitely. I'm pretty sure that's the case. It can be complicated to quantify. And so for our study on the CQ relations in Quebec in particular, another reason why we're focused on only 32 watersheds is because those ones are mostly in southern Quebec where we have complete LiDAR coverage. And so we can actually look at the streams to see whether we can actually see obstructions. And given that some of those rivers are pretty large, the LiDAR resolution is fine enough. It's 1 meter everywhere that we can actually basically hunt for those obstructions and try and see whether that explains some of the differences in behavior that we're seeing. So yes, absolutely. Quebec is also really, really good. Like we're discovering a bunch of, well, they're new data sets to me because I hadn't worked in Quebec for quite a few years. But in there, they have a quote unquote hydrographic network data set that is publicly available, where all sorts of obstructions are actually mapped with their connections to the landscape, regardless of whether this is in-stream or on land as well. And so we just need to incorporate that data into our CQ analysis to see whether that can help explain and shed light on some of the strange results that we're seeing, absolutely.
Hi, I was just wondering, when water quality monitoring is done, there's trade-offs between how many sites there are, how detailed your analysis, how often you measure. So for the purposes of the type of CQ analysis you're trying to do, I was wondering what your opinions are on what should be prioritized when setting up these monitoring plans.
Oh, Lord, okay. That's a big one. I don't know. I think, and this is going to sound like I wouldn't actually say that to my stakeholder colleagues because they would scoff at me. I think that ideally we should always start with the higher frequency possible and then decrease. Because if you think about the theoretical models, for example, if you were to do high frequency sampling for a little while and realize that, oh, it's very likely that I have a chemostatic regime, then you can probably sample once a month or once every 2 months, and that's fine because you have pretty much quasi-invariant concentrations despite different flow conditions. Whereas if you're dealing with I guess a chemodynamic behavior with a dual slope, and then maybe one is like below the threshold you have enrichment, below the flow threshold you have enrichment, and above the flow threshold you have dilution, or vice versa, then that becomes really, really complicated to be able to make sense of data that would be collected only once every 4 or 5 months or seasonally, right? And so I don't think we're there yet in terms of proposing or suggesting an ideal monitoring frequency, especially because it may very well be water quality parameter dependent. That being said, I think that something that Quebec is doing that is working really, really well as well is that yes, it's provincial data, but the sampling is quote unquote dispatched on the watershed organizations. And so those are the ones responsible for going out at least once a month. And then there is a streamlined process for them to send the samples to a government lab. And so that is what has allowed them to maintain that monthly sampling frequency for quite a while. Like there's some sites that have been sampled at least once monthly for more than 20 years or 25 years, which is pretty cool for us to be able to use, especially given the really wide range of water quality parameters that they're including. But yes, I agree, those trade-offs are always very difficult to find. And sometimes it's really about what is the minimum number of data points you need in any given year if your goal is to estimate loads versus your goal is to estimate potential sources or runoff mobilization mechanisms. I think that the answer would be different depending on what the ultimate goal actually is.
Great. So I'm seeing no more hands. We are at 10 o'clock. So let's have another round of applause for our new lecturer.